Previously, we learned how to find the electric potential at a point when we know what the electric field expression is. Now we're going to look at some very specific electric field expressions and derive an expression for the electric potential due to those electric fields that are set up by the charges. In this first video, we're going to look at how to find the electric potential at a point when a point charge is the thing creating our electric field. To do that, we're going to look at something very general to start off with. We're going to consider a point charge Q naught. That's this positive charge that you see right here. And we're going to say that, Q naught is not this positive charge here. Q naught is this positive charge up here. We're going to say that we're moving this positive charge Q naught from a point P, which you see on the diagram right here. And that point P is located at a distance of capital R from our source charge, or the thing creating the electric field. We're going to move Q naught from the point P to infinity, and it's moved to infinity by an electric force along a straight path. And so if we're trying to find the potential difference, specifically delta V, we know the general expression for potential difference is the negative integral of E dot dr. And this time we know specifically that we're going from the point P, which is located at a distance of capital R from our source charge, to infinity. We'll put limits right on that integral. Now, if I think about the direction of the electric field, since the electric field points away from our source charge here, since it's positive, so it's pointed upward, and since we know we're moving our little test charge from the point P to infinity, which means we're moving it straight up, E and dr are in the same direction. So when I evaluate that dot product, which we know becomes the magnitude of E times the magnitude of dr times the cosine of the angle between the two, this angle between the two is 0 degrees, and we know that the cosine of 0 degrees is equal to 1. Next, I'll plug in an expression for E, and we know E that is created, or the electric field created by a point charge, is the equation KQ over R squared. When I plug that in for E, and I have my dr here, I see that it's an integral that we can take relatively simply. I'll start off by pulling out my constants, which are K and Q. And then I have the integral from capital R to infinity. I have 1 over R squared, which can also be expressed as R to the negative 2 dr. And when I take that integral, I get negative K Q times negative 1 times R to the negative 1 power, evaluated between capital R and infinity. So this negative in front of the KQ and the negative in front of the R kind of cancel out. I'm left with the expression KQ over R, evaluated between capital R and infinity. And we know that we plug in infinity first, and then we plug in R. When we plug in infinity, I get an expression over infinity, which is basically 0 minus what I get when I plug in capital R, which is KQ over capital R. Now again, remember, this was deriving an expression for delta V. But really what we want is the electric potential at the point P, not the potential difference. And potential difference is final minus initial, right? Well, the initial is the thing we're looking for. The final we know would be equal to 0 because we say that the electric potential at infinity is 0. So really, I have 0 minus V initial is equal to 0 minus KQ over capital R, which means the electric potential at that point P, the thing that we're trying to derive, is KQ over R. In this case, the problem used a capital R, but quite often we use a lowercase r in our total expression here. Now that we've derived that expression, even though you should know how to get there, you are welcome to use V equals KQ over R. Or more specifically, we know that when We're allowed to use things that are on our equation sheet. And so on the AP equation sheet, it's expressed as V equals 1 over 4 pi epsilon naught, which we know is just another way of writing K, times the summation of Qi over Ri. Now, the reason you see the summation and the expression on the equation sheet, rather than just saying KQ over R, comes from the fact that when we're trying to find electric potentials with multiple point charges, we are simply allowed to add the KQ over R for each charge. That comes from the fact that electric potential is a scalar, not a vector. So it's a lot easier to deal with multiple charges and finding electric potential than it was to deal with multiple charges and finding electric field. Let's take a look at that. This is an example problem from your textbook. It's problem number 17 in chapter 24. We see that there are 4 point charges here, and we're looking for the electric potential at point P due to these 4 point charges. Now, before you jump right into trying to calculate this problem, it actually serves you well to think quite a bit and think in terms of variables rather than numbers. It actually reduces the work quite a bit for this problem. So we know that we always want to start with a general expression that we find on our equation sheet, which the equation sheet basically says that V is equal to 1 over 4 pi epsilon naught, which again we know is the same thing as K, times that summation of Qi over Ri, right? So I'm going to think about the fact that I'm adding together the electric potentials of each of these 4 charges. So I'm going to write this expression in terms of variables rather than using numbers to start off with. And I'm going to use K instead of 1 over 4 pi epsilon naught just to reduce what I need to write. I'm going to go ahead and label them so I can talk about them easier. I'm going to call them 1, 2, 3, and 4. So I have K times positive Q over D for charge 1 plus K times positive Q over D for charge 2 plus K times negative Q. So I'll put that negative out front. Negative KQ over D for charge 3 plus K times negative Q, or negative KQ, over 2D for charge 4. Now, thanks to the fact that these are scalars, it's pretty easy to see that this KQ over D would cancel out with this negative KQ over D. So we're left with just adding together KQ over D minus KQ over negative D. That gives us a positive KQ over 2D. Now that I've come up with this expression, it's much simpler to plug in numbers to get my final electric potential at this point. And I trust that you can plug those numbers in your calculator to get the value 5.62 times 10 to the negative 4th volts. Electric potential is definitely one of those times where I encourage you to find your expression in variables first before plugging in numbers, because quite often it'll save you quite a bit of time in plugging those numbers into your calculator. We'll practice more with finding electric potential from point charges, and in future videos or in class, we'll learn about how to find the electric potential when you have a continuous charge distribution rather than point charges.